5E problems. We're going to talk about conservation of energy. And I want to kind of alert you to how we're going to handle the rest of this chapter. A few of you noticed ever so sneakily that there is a 5F section of problems, which is power problems.
That's that got ripped down my butt.
Yeah. Well, before you get too excited there, Dorothy, we're not going to do the math on 5F. We're going to do power conceptually. We're going to talk a little bit about it. I'm going to give you the equations, but we're not going to do the problems. The reason being, we need to hurry our little selves along to. Well, no, we're not doing 6. We're moving on. We'll do a conceptual discussion of 6, but we need to hurry ourselves along to springs, wave behavior, sound, light, and then circuits and current. 12, 13, 14, 17, 19, 21. Huh? Doesn't happen here.
We're going to talk about like ohms and stuff like that?
Yep, that's circuits.
That's
Okay, so this is a basic physical science concept, conservation of energy. You know conceptually that neither matter nor energy can ever be what? Created or destroyed. But we sure do trade back and forth a lot. Roller coasters, gravitational potential energy. First hill is the highest. Why? Okay, you get less and less energy every time. Where is yes, or as they say, that. Where is that energy going?
Down and up and down and up.
Okay, so at the top of the first hill, you have lots of gravitational potential energy. As you go down that first hill, it's all translated into kinetic energy. Then you come back up a little hill, and you've got, again, gravitational potential, but you've also still got kinetic because you're moving. And the overall amount of energy does what as time goes on? The overall amount of mechanical energy in the system does decrease. But I thought we said energy was never lost. How could it decrease? Where did it go? This is so sad. Where'd it go?
It transferred
To
Thermal.
thermal energy. Okay. Okay, so we've got a couple places that mechanical energy goes. Some of it gets transferred to thermal energy. The tracks heat up. Now, I don't know that you could fry an egg on the tracks after the roller coaster goes past, but you certainly don't want to lay your bare hand on them for too long. They're going to be pretty warm. There's another place that goes.
Screaming. These guys are getting fun.
Okay, so we have a transfer into thermal energy. We can have transfers into light. So heat, light, and sound are the big ones. Sound is a vibration. Sound is movement of air molecules or other molecules. Sound is actually a form of energy. And so the sound that you're hearing as the train goes past, that is also a place where the mechanical energy is lost too. But the big one is heat, generally. So heat, light, sound are the big places we lose mechanical energy. In a perfect world, no mechanical energy is ever lost. However, we don't live in a perfect world. Okay. When we talk about this, what we're talking about is mechanical energy, ME. It is the sum of the kinetic and potential energy in any system. We can have kinetic energy, gravitational potential energy, and elastic potential energy in a system. Yes, doesn't that sound like fun? And when we add up all the forms of potential energy, or all the forms of mechanical energy in a system, we get the total mechanical energy. We do not cover anything here but kinetic and potential. That's it. So other things, the energy that's stored in gasoline, that is a form of chemical energy. It's sometimes referred to as chemical potential energy. That is beyond our scope to compute that stuff. If anybody here is doing chem engineering, you'll do lots of that, but we're not going to do it here. The energy associated with light, We did a little bit of that in chemistry with Planck's constant and wavelengths, frequencies, energy. We're not going to do that here. Nuclear energy. So the energy that's contained in the atom that we get out of it by splitting the atom and we turn on light bulbs with. Don't get me started about that. Those are all non-mechanical forms of energy. We are not going to compute them here. They're beyond our scope and our abilities, and they're just outside the realm of this course. Okay? We're only going to refer to them. So we're going to talk about non-mechanical energy. The heat and the light and the sound, where you lose mechanical energy, those are also called non-mechanical energies. They're hard to capture. So they're hard to capture, and they're not something we're going to be computing. Are you familiar with piezoelectronics? Okay, we'll save that for another discussion. Actually, look it up on your own. We'll talk about that another day. It relates very much to mechanical energy and electrical energy. So, but we're not going to cover it here. P-I-E-Z-O. Piezo? P-I-E-Z-O. Okay. So, I believe, there we go. All right. So, in thinking about that conservation of mechanical energy, we can look at initial mechanical energy in a system. We can look at final mechanical energy in a system. If we lived in that perfect world, guess what? They'd be equal. But we don't. So, they're not. We tend to ignore that. So, that won't get you by in an engineering class, those of you who are going on engineering classes. But at the level of high school physics, we just ignore mechanical energy loss in systems. We pretend it doesn't happen, unless we're doing a problem where we're thinking about it. But we most often, as long as it's small, we forget about it. Okay, so that's what I thought was going to happen. Good. So now